Hello and welcome to Agents of Tech, our brand new science and technology podcast. I'm your host, Autria Godfrey.
And I'm Stephen Horn.
In Agents of Tech, we are looking at exciting new technologies that are shaping our world and our lives today, from big data and quantum computing to AI and robotics. We are taking a deep dive with some of the best minds working in science and taking a look at how their research could transform our lives in the future.
I've been in Las Vegas, Nevada at the American Physical Society's March meeting. It's the biggest physics conference in the world with over 10,000 attendees. I met with Gabriela Gonzalez from Louisiana State University, who works to understand phenomena she describes as physics magic, gravitational waves. It truly is the story of where our universe all started.
Well, first of all, thank you very much indeed for joining us this morning. We really appreciate it. Thank you.
Thank you for inviting me. This is great.
Let's start off. Tell us, what are gravitational waves?
We like to say that gravitational waves are ripples of space-time. And this is a bit difficult to imagine, but this is how Einstein imagined gravity, that the sun disturbs the space-time, it curves space-time, and that's what makes the Earth go around. But now if you have two objects, like two black holes going around, then they are producing waves of space-time, and those are the gravitational waves.
And these were predicted by Einstein? Or?
They were. He published his theory of general relativity, which is a theory of gravity, in 1915, and in 1916 he published a paper that had some mistakes about gravitational waves. But because of the constants in the theory, Newton's constant, speed of light, the amplitude of these gravitational waves were very small. And he said something in the paper about that, and he didn't think about this until much, much later.
What got you involved? What got your interest?
I was interested in general relativity, in Einstein's theory, since I started college. And I like that. And but then when I heard about this project, this was in the early 90s, a long time ago, when I heard about this project that was building these big detectors to measure these very tiny distortions of space-time going through Earth, I thought, that's magic. That's physics magic. So that's what I did. And I've been doing it ever since.
Let's talk a little bit about your own areas of research. So within this field, what are your own areas of research?
Well, I have done a little bit of many different things, but mostly related to the instrument itself. The instruments we have are interferometers. They use light to measure distances, lasers, and the technology that we use is very, very complicated. And I have been involved in putting it together with many, many other people. We are big teams in general. Lately, I have been also more involved in looking at the noise in the detector, what produces the noise and how we can make it more sensitive.
Tell us a little bit more about the equipment itself. We called it LIGO, don't you? Tell us what that stands for, and tell us just a little bit more about kind of how it works.
LIGO stands for Laser Interferometer Gravitational Wave Observatory. LIGO is a lot shorter. And what we use is a laser that we split in two to travel very long distances, 4 kilometers, that's more than 2.5 miles. And then the beams come back and they interfere. That's why we call them interferometer. And the interference pattern depends on the distances they have traveled. So if there is a gravitational wave, it will make this distance shorter, this one longer, and that's what we measure on a photodetector that measures the interference. Now the distances that we measure are tiny. We make them long because the longer the interferometer, the larger the signal, but the signals we have measured are a part in 1,000 of a proton diameter.
Tell me, how did the idea come about? How did you start off with the concept to do this?
Well, I didn't start with the concept of interferometers. In fact, it was in the 70s when people began thinking about how to measure gravitational waves. And there were different ways. There were resonant bars that would vibrate with a gravitational wave, and there was this idea of interferometers that Kip Thorne and Ray Wise at Caltech and MIT, respectively, thought it was going to be the future. They knew it had to be long, they knew it had to be expensive, so it took 20 years for the project to get funded, but they got it. And I'm very glad I got into there when the detectors were beginning to be built.
So you said it took 20 years to get it to get it going. So let's go a little bit further forward. So 2015, I think it was, when the black holes were discovered, the waves, if you like. What was your thoughts and emotions? That must have been such an incredible time.
It was an incredible time for many different reasons. We had operated a first generation of technology in the 2000s, and we had installed the second generation, and we were beginning to operate it in 2015, but we had no experience with this new instrument. And in one of the trials, just before we began taking data for sure, we saw this signal and picked up by computers comparing signals, and these signals seemed to be coming from two merging black holes, which nobody had seen before because they're black. So they don't emit light if you have two black holes. So we thought it was incredible. In fact, we thought it was too good to be true. It took us several months to convince ourselves that this was a real signal.
How did you convince yourselves?
Well, we had to take more data because this was a new instrument. So we didn't know what the noise looked like, and we couldn't tell if the noise looked like this signal. It might have been. We have all kinds of different noises, even with transients. But this was a coincidence between the two LIGO detectors in Hanford, Washington, and Livingston, Louisiana, 3,000 kilometers away. So it was unlikely, but we had to be completely sure. So we took a month of data, we analyzed that, we compared it with models of black holes. We looked at all possible reasons, including hackers. That this was not,
of course.
It was not a fake signal, and we made the announcement in 2016.
So what are some of the technical challenges that are involved? I know it's something quite dear to you, close to your own heart, your own research. So what are some of the technical challenges?
Well, when these instruments are designed, then you know what to expect. And we know that we are limited by some kinds of what we call fundamental noises, which is how much the Earth moves, which moves the mirrors that reflect the laser light, how much the mirrors move due to Brownian motion, and the quantum noise in the light, because we use a laser.
Right.
So those are our fundamental noises. But to get to the level of the fundamental noises, we have to eliminate all kinds of other technical noises, including the electronics, the feedback control systems that we use to make this very complex interferometer work, and that takes years.
And how are you facing up to those challenges? How are you doing with those challenges?
We are doing very well. In fact, we have already detected 90 different signals, and not all from black holes. We have also detected two coalescences of neutron stars, two coalescences of neutron stars and black holes. And in fact, we have some of these coalescences and some of the masses we have discovered are in what we call a mass gap, which are between masses of neutron stars and black holes. So we are feeling the spectrum. It's been great. But to do this, we need to make our detectors more and more sensitive, and we are using sophisticated quantum techniques. We are working on these technical noises that are always there, and we are actually now thinking of new detectors, next generation detectors that would be bigger, longer, and 10 times more sensitive. We would be able to see black holes from the whole universe.
Let's talk a little bit about that. So you're talking about technological advances coming up. Talk us through that. What a bit more detail on what those advances are likely to be.
The biggest difference between these detectors and the next generation one would be the size, because Einstein's theory says that the longer the distance you measure, the larger the change in distance, which is what we measure. So our detectors now are 4 kilometers long on each arm, and we are dreaming about detectors that are 10 or 20 or 40 kilometers long. So even if we use the same technology that we use now, that would be more difficult on that on that length scale, we would be more sensitive. But we are also looking at new materials to reduce the effect of the Brownian motion of the mirrors, at new quantum optics techniques to reduce the quantum noise of the laser. And we are beginning to use a lot of that.
How fundamental is quantum physics to what you're doing?
It's very fundamental, but it's not just quantum physics. It's quantum physics and gravitation, which Einstein theory is a classical theory. So we are measuring a classical effect, but we are measuring it with quantum optical techniques. So I love this mixture of all of physics in our instrument.
So it sounds to me that it's very collaborative, the work that you do. You must be working with a lot of different people, literally all around the world. Is that right?
We do, yes. I am a member of the LIGO Scientific Collaboration, which has members from about 100 different institutions worldwide. But we also work with the LIGO, with the Virgo collaboration in Europe and with the CAGRA collaboration in Japan. So all together, we are about 2,000 people. And we need that not only because we need detectors in different places to triangulate the signals. We have the 2 detectors in the US, the 2 LIGO detectors, but we work with a Virgo detector in Europe. And we had a spectacular discovery with them of 2 neutron stars colliding. But we will be working with this Japanese detector, CAGRA. So we are doing all of that. But we need people who develop new technologies. We need people who implement those technologies and make the detectors work. We need people who look for the right codes to look for the signals. We need people who interpret what we get from the signal, saying these are black holes, these are spinning black holes. And that's why we need all of them.
It seems as well to me that it's quite a big funding challenge, must be, to get the money for this advancement in technology. People and skills.
It is a very big investment, and we are very grateful to taxpayers for investing for a long time in this experiment, because when the detectors were built, there wasn't a guarantee that there was going to be a detection. In fact, it was believed, and it was true, that the first generation would not detect gravitational waves, that it would have to be a second generation, which is exactly how it happened. So this was a funding for more than 20 years by the National Science Foundation in this project. And now, of course, we are all excited and we know that investment was worth, and now we want to be bigger. But there are so many things, so many good things to invest in physics.
What do you think you're going to find? And this is an impossible question to answer, but what do you think you're going to find next? Or what would you be most excited about finding next?
Well, we look for not just coalescence of neutron stars and black holes, which is what we have found so far, but we also look for sinusoidal signals from rotating neutron stars in the galaxy. We look for a stochastic background of many signals mixed up with each other. But what I am most excited about is finding a new signal, finding something that we didn't expect.
Well, thank you very much indeed for taking the time to talk to us today. Absolutely fascinating, very exciting. We're very grateful for you taking the time. So thank you.
Thank you for the opportunity.
That is absolutely fascinating. And I think what I loved the most was her story about how when they first detected the signal from 2 black holes merging, they thought that it was just simply too good to be true and that they might have actually been hacked. Of course, that's everyone's first thought. We've been hacked. Truly, though, incredible achievements.
Truly incredible, wasn't it, Autria? And humbling as well. Now, my next guest is a man who has achieved at the very highest level. Anton Zeilinger, 2022 Physics Nobel Laureate. He spoke to me about his incredible contribution to physics, his work in quantum entanglement.
First of all, thank you very much for talking to us today. Very much appreciate you taking the time, so thank you.
Well, thank you for the invitation to talk to you. And maybe some people like what they hear and see.
I'm sure they will. So obviously a huge honor winning the Nobel Prize.
Well, you know, it takes a while until you realize what the impact is, you know. It was actually interesting, you know, as Nobel Prize winner, they call you 1 hour before to inform you that this is coming up, and so you can get ready for the zillions of mails and requests by press and so on, which are all very legitimate. But when they called me, it was the General Secretary of the Swedish Academy who called me. He said, "This is not a fake."
Not fake news.
It's not fake news. Yeah.
Tell us a little bit about the experiments that you conducted that you won the award for.
It's all about entanglement, about the fact that two or more quantum systems can be connected in a way which is still strange. They can be connected without any connection between them and without any information being sent around. So this is a very, very fundamental property of our world, a property which we probably have not fully grasped yet what it means for our understanding of the universe.
Very exciting to be at the forefront of that.
That is exciting, and that was my motivation for many years. And maybe I could say that in the beginning it happened to me, but also to the other two Nobel Prize winners, John Clauser and Alain Aspect, that our work was not seen as very serious, just philosophical, and something which the forefathers of quantum physics have been taking care of, and why do we bother with it?
Why do we bother with these things?
Well, for me it is just curiosity. Curiosity is for me the only motivation.
What are some of the phenomena that have come out of your work? I mean, in terms of how has your work paved the way for some of the more sexier applications, the quantum computers, the cryptography, or that sort of stuff?
When we talk about applications, then that is something which actually totally surprised me. When we started our work, in my case, I was rather late. I started my work in the late 1980s, compared to the other two Nobel Prize winners who were there earlier. And when we started that, when somebody asked me what this is good for, I told them I can proudly tell you that this is good for nothing. If I was wrong. People invented applications like quantum cryptography by Charlie Bennett and Gilles Brassard, and entanglement-based quantum cryptography by Arthur Eckert in England. And when that came out, I thought this is very, very interesting. But I still thought this is just a curiosity and not an application.
One of the things, we've been sat here all week talking to people who have been given lectures and who have been doing research. And if I had $1 for every time somebody said quantum to me this week, I could retire a rich man. Where do you think we are now in quantum? Where do you think, what's most interesting to you, and where do you think we're positioned?
Well, to me, the most interesting questions are still the open fundamental questions. Like what does it all mean? And there are still things hidden which we have not really addressed yet. In terms of applications, I find these applications, the more exotic, the more interesting I find things. Like these ideas of having worldwide quantum networks using satellites and so on. These are just fascinating because it's technically sweet, It's just very interesting to do this, About the quantum computing experiments, I'm heavily impressed what people are doing now and what they can achieve compared to 20 or even 10 years ago. This is just mind-boggling.
Where's your work taking you now?
Well, my work is taking me still towards foundations. I'm still interested in, whether this entanglement, which we see, could be something which has been predetermined by some earlier cosmic events, which we don't know yet, This is an interesting. It's also an interesting experimental question because you have to look for sources of randomness in the universe, which come from very, very far away, very far at the beginning of the universe. This is one of the things, and I'm still interested in what quantum physics tells us, or what the physics of multi-particle entanglement tells us about our understanding of the world. There's still a lot open. It's interesting.
One of the fascinating things this week has been talking to physicists about gravitational waves and looking at, as you were saying, in terms of black holes colliding, a billion years ago. It's a very interesting time to be studying what you're studying, to be researching what you're researching.
I'm lucky to live at this time when so much happens. You mentioned cosmology. There's a lot going on in astronomy, astrophysics. Like just recently, they discovered some galaxies which existed very close after the Big Bang, and which, according to our understanding of the dynamics, should not exist. I mean, this is so great. This is the great thing in physics, that what we believe today might be overthrown tomorrow, not because of some personal prejudice, but because nature tells us.
Must be important to keep an open mind then.
I think it's very important to keep an open mind, and it's a challenge, because you also have to have your own convictions, because they motivate you for what you do. And the question, when do you know that you have to give up your convictions? It's very difficult. It's a personal judgment. It can only be done by a person himself or herself, and not by the community.
You're giving a lecture on Thursday, I believe. Can you give us some idea of what you'll be talking about?
Well, I will be talking certainly about the path of experiments which we did, like, a very well-known kind of experiment was quantum teleportation, where you can teleport a quantum state from one particle to another one over arbitrary distance. Another one is called entanglement swapping, where you can swap entanglement between different particles. This is actually quite essential technology for communication between quantum computers. People think, I will also talk about the question for how large systems can you expect quantum phenomena? This is an open question, and to me there is no limit in principle. It's just a challenge, just a huge challenge. And I will talk about what this all means,
right,
in my opinion.
What does it all mean in your opinion?
In my opinion, it means that information is a more fundamental concept than reality. Information in the sense of what can in principle be known through experiments, through observation.
Do you think we do enough work, or we pay enough attention to the principles as opposed to what we can do with them?
Well, that's actually amazing. The whole field started because, like, maybe a dozen or maybe 2,000 people in the mid 1970s. There were maybe about 2,000 groups, if it were so many worldwide, interested in these fundamental questions. And that actually made all this quantum information field possible. And now the interest and also the financial support for fundamental research has gone down. And that is not a good development. First, because it doesn't answer our curiosity. And secondly, I'm pretty sure that new fundamental discoveries will open up and pave the way for new possible applications.
We're obviously at a very early stage still, aren't we? Do you think there's so much more we've yet to find out?
Well, when we talk about the understanding of the world, I like to say that humanity exists certainly on the scale of 100,000 years or more. We do science, modern science, for about 300 or 400 years, since people like Galileo and Kepler and Newton and so on. Newton was the founder of physics as a mathematical science. So this is very small. So it's like only the peel of an orange. If we would believe that we have covered and learned, the most essentials yet, that is just demonstrating the limits of a fantasy.
One of the questions that I wanted to ask you was about young people in physics. I'm really struck by what you've been talking about in terms of curiosity and how that's always been your driving force. And how do young people starting out who would be listening to you on Thursday, what should their next step be?
I only can talk about my own experience, and that is that I had the privilege to be able to follow my nose, which was not the nose of many others, And I did it because I was curious, and I was lucky to get the support for that. When young people come to me and ask me what to do, I ask them first, is there something you are really interested in? And if there is something like that, do it. Because, you will be rewarded in your life for that. And if you are excited by what you are doing, you will also kind of professionally be better than others who are not so excited as you are. So just follow your nose. I know this is not easy. And it was also very important, to join the right group which fits to you. Where is a possible supervisor who might join you, might share at least your interest and let you work,
My final question is how important is it in physics to have meetings like this, where so many people from all around the world are coming together to share these ideas?
I actually have been to a couple of these meetings of the American Physical Society. And it's always interesting to hear people talk and present their stuff, and you only can listen to a small fraction of what's possible. But at least as important is that you meet people in the hallways, You suddenly talk to them and you change a few words, and then you see, very interesting. But, yeah.
It's been such a pleasure talking to you. We really appreciate your time, and I hope you enjoy the meeting and that your lecture goes well tomorrow. And yet again, congratulations on winning such a big prize. Thank you.
Thank you very much.
So the career advice there from a Nobel laureate: follow your interests and be curious.
Good advice indeed, isn't it, Autria? As Anton says, follow your nose, and you might just discover something that contributes to our understanding of how the universe works.
I love that. Follow your nose. Well, until next time, goodbye, everyone.
Goodbye.